Good morning to all. Welcome to chemistry class. So in our last class, we have discussed about entropy, and we have written few formulas also, and we have discussed about entropy and its formulas also. So what was the conclusion in our last class? We shall glance that one. That is delta S is equals to Q reversible by T. That was the formula we had written. Change in entropy is equals to heat absorbed in the reversible process divided by temperature. One more formula we have discussed, that is delta S universe is equals to delta S system plus delta S surrounding, and which is greater than 0. So suppose if at all if it is greater than 0, then it is entropy is increasing and the process is spontaneous. So that is that point is here. So delta S universe or delta S total it is. If delta S total is positive, then the process is spontaneous. If delta S is negative, then the process is non-spontaneous. If delta S is equals to 0, then the process is in equilibrium. So that is what we have already discussed. And one more point, if delta S is positive, when the system absorbs heat at lower temperature rather than at higher temperature, that is nothing but, so when system is in lower temperature, so if the delta S will be more increasing if you provide the temperature to it, if you provide the heat to it. So the substance or the system is at lower temperature, so absorbs heat, and delta S will be more for that one than the system at higher temperature if the same amount of heat is provided to you. That means that, so delta S for a system, if you are considering, delta S for a system is inversely proportional to temperature. Clear it is? So the first point, that is more important. So the lower the temperature of the system, delta S will be increasing. So we'll move on to the next. This was the conclusion of our last class. So by this, all these formulas or all these concepts of entropy and all. So we are going to define the second law of thermodynamics. Before that, we have few more formulas of delta S. So we shall see that one. So we have already, all these are of entropy formulas, entropy related formulas itself. So we are going to discuss about that one now. So entropy of solid is less when compared to entropy of liquid, and that is less when compared to entropy of gas. So if you consider the entropy here, so the entropy of solid is less. Entropy is nothing but randomness. For a solid, randomness is less, and for a liquid it is little more than the solid, and the randomness is more for gas. So this is very, very important when you consider any reactions. So problems will be asked for this one. So now the second one, that is delta S is directly proportional to change in volume. That is, change in entropy is directly proportional to change in volume. So let us consider an example. So if at all, if it is, so if we are considering if we are considering an if we are considering an container, that is an container we have taken, and the container is filled with gas. Let us think a piston is there and we have filled that one with an gas. So gas particles are here. So some 5 gas particles will write. Clear? So now we are going to increase the volume. So volume of the container we are going to increase. The piston we have moved upward. Let us take here the volume has been increased. Now the same 5 particles only, but you can observe the 5 particles are very far from one another. Randomly they are moving. So here you can observe they are very close to one another. As the volume has increased, so the randomness also has been increased. So we can say that delta S is directly proportional to volume, and this is an important formula. So mark it down. All these are from NCERT only. All these formulas, all those are in terms of explanation it is given. But we have written that one in the form of one formula because it is important for problems especially. So that's why we have written in terms of this. So delta S is directly proportional to change in volume. As the volume changes, entropy, change in entropy is increasing. So they are directly related. Now delta S is directly proportional to delta Ng. So delta Ng is nothing but number of gas particles. So suppose delta Ng, let us take delta Ng is greater than 0, or it is a positive value. If delta Ng is greater than 0 or delta Ng is increasing. So that indicates that greater than 0, that indicates that the particles are, rather than taking that one as 0, let us think. So the number of particles in one of the system we have only 5, and in another system we have some 10 particles, 10 molecules are there. So the 5 will be showing less randomness when compared to 10. So we have considered one more example, that is in a classroom. So if 10 students are there, then the seating arrangement, we were about to change the seating arrangement of the students. 10 students, the seating arrangement, if at all, if you interchange with one another, so the number of probability of changing the seating arrangement will be less when compared to a classroom with 20 students. If 20 students are there, double than that or more than the number of 10 students, more than that we can change the places. So that is nothing but the randomness or the changes will be more if the particles are more. If the particles are less, so the randomness or the disorderness is going to be less. So that's what we have written. If delta Ng is greater than 0, then delta S also will be greater than 0. Clear it is? So now in this case, so delta S is greater than, delta S is directly related with change in temperature. So don't get confused with the temperature alone. So we have one more formula, so that in our last slide we have seen, that is delta S we have taken, and delta S is inversely proportional to temperature. That is for system we have written. So delta S is inversely proportional to temperature. But here a system we have taken. Let us take this as a system. Volume is fixed. We have a container. We have taken a container. So 2 containers we have taken. So the particle is at temperature T alone here. Same, both the system is at temperature T only. The particles are there. Same number of particles we have taken. Clear? Now, so both are in temperature of T1 itself. Now we are going to increase the temperature. So the temperature of T1 remains as it is for this container. Here we are going to increase the temperature by 100 Kelvin. We are going to increase that one by 100 Kelvin. Clear? So along with T1 temperature, we are increasing the temperature by 100 Kelvin. Then kinetic energy of the particle increases. When kinetic energy increases, so the random motion is also going to increase. Earlier the temperature was T1 only. Here also temperature was T1 only. So the change in temperature is 0 here. The change in temperature is 100. Clear it is? So the change in temperature is T1 here, or the change in temperature is 0 here. That change in temperature is 100 here. As the temperature changes, as the temperature is increasing, so the randomness is also increasing. So when we have discussed this part, at that time both the substances were not in same temperature. They were in different. So the first system was in lower temperature, second system was in higher temperature. So at that time the change was more observed in the case of lower temperature and less was in the case of higher temperature. Now what we are taking for this one, what we are using is, the condition is both the system are in the same temperature and the temperature is T1. So now we are changing the temperature. The first system temperature remains as it is. The second system temperature we are increasing. We are increasing. When you have increased the temperature, randomness is also going to increase with the increase in kinetic energy of the gas molecules. So delta S is directly proportional to change in temperature. Next, delta S is directly or inversely proportional to or proportional to 1 by delta P at a given temperature. That is nothing but temperature is constant. If temperature is constant, then delta S or change in entropy is proportional to 1 by P. So if at all, if the process is at constant volume, if you are taking the process at constant volume, then delta S is directly proportional to delta P. Clear? So all these formulas, you remember all those formulas. It is very, very important. Next, we'll move on to our second law of thermodynamics statement. So until now we have discussed about all the basic things to understand what is second law of thermodynamics. So all those concepts, formulas, everything we have understood now. So now we are going to define, or we are going to check the statement of second law of thermodynamics. So remember, second law of thermodynamics have many different statements based upon the processes which we are going to discuss. Now, all those statements are some 3-4 statements I have made here. So all those statements we are going to discuss now, and it is based upon the processes or the things which we have discussed earlier. Clear? So first law is based upon conservation of energy. So second law tells us about the processes which is taking place in the universe, or the spontaneous processes. It is the spontaneous or feasibility of the processes it is checking. So we shall check that one. The first statement, entropy. The entropy of the universe always increases in the course of every spontaneous change. That is nothing but, so when you consider the universe, so universe is neither losing energy outside nor it is gaining energy. But whatever the natural processes are taking place, all those natural processes are spontaneous in nature. So all these natural processes are taking place in universe. Universe is the system. If you consider, all those natural processes are spontaneous and which is taking place in the universe. So for all those spontaneous processes, we have already studied delta S is going to increase. Delta S is positive, or delta S is increasing. So that's why, so all these processes where it is taking place, it is taking place in the universe. All those natural processes are taking place in the universe. So all those natural processes are spontaneous, because of which entropy is increasing. So entropy always increases. Clear? So because natural processes are spontaneous in nature. Clear it is? So the next statement will move on to. So second statement, all spontaneous processes are naturally occurring processes are thermodynamically irreversible in nature. So that is already we have discussed. If a water is flowing from an up a hill, so it is flowing down a hill. So it is from the hill, the water is flowing down. So if at all, if it is flowing down, so the reverse process is water flowing back upwards. Water flowing back upwards, which is not at all possible. So unless you fix a motor, water cannot be lifted up. I hope it is clear. Water can flow down easily, but flowing towards upward is not at all possible. Without the help of anything, it cannot flow upwards on its own. Likewise, so a cup of tea is kept on a table, an open cup of tea is kept on a table, so that after some time, if you check, the temperature is very, very less, or the tea has turned out to be cold. So that is the spontaneous process. So the tea was a hot body. From the hot body, the heat is being heat is being traveled, or heat is being moved towards the surrounding, which is the where the temperature is very, very less. Clear? So when you consider the cup of a tea, it was very hot, or it is an hot substance. So heat is being, it is being transferred to the surrounding, which is at a lower temperature. So if at all, the reverse of that one is flow of heat from the surrounding or from the atmosphere to the cup of tea, which is not possible. Which is not possible. That is what the statement says. All spontaneous processes are naturally, all natural processes are spontaneous in nature, but the reverse of that one is non-spontaneous. Clear? Next statement will move on to. So without the help of an external agency, a spontaneous process cannot be reversed. That is what we have discussed just now. So without the help of an motor, water cannot water cannot flow from downward or from a lower position to upward position. So that is the external agency. Will we are what is meant is, what we are meaning here, external agency is nothing but, so the pump which is going to help throughout the process of lifting the water from downward to upward. Clear? So that is the reverse process. So water lifting from or water moving from downward position to upward position, or down the hill to up the hill, it is an reverse process. So to do that reverse process, so we need an external help, and that external help here, it is a pump or motor. Clear it is? So without that, it can't be reversed. Next statement. The complete conversion of heat into work is impossible without leaving some effect elsewhere. That is nothing but whatever the heat is supplied to the system, so it can't be converted, entire amount of heat cannot be converted into work. So that means that, so heat is being utilized, but that entire amount is not utilized as a work. When you take a fuel there, so when you take an engine, or when you take a vehicle, automobile there, so whatever the fuel you are using, that entire amount is not being converted as work. So that is what we call as mileage. In our normal words, we are using a term as mileage. That mileage indicates that the substance, whatever the amount of fuel is there, so how much amount of that fuel is being converted as work. That tells us about that mileage indicates that one. So in normal or general reaction also same thing. So whatever the amount of heat we are providing, that entire amount of heat is not being converted as work. Some amount is being wasted, or some amount is being utilized for some other purpose. Clear it is? So we'll move on to the next part. So to understand this one, we'll understand the concept of entropy by using a problem here. So it also tells us about the limitations also. Second law we have studied. All those are the second law statements. So all those things we have studied. So what are the limitations of the second law also we'll study by using an problem which is there in the NCERT syllabus. So we'll study about that one also. So we have a problem, that is iron is being reacting with oxygen and it is forming Fe2O3. An entropy change is being observed, and that entropy change is minus 549.4 kilojoule, joule per Kelvin per mole at 298 Kelvin. So in spite of negative entropy of this reaction, why is the reaction spontaneous? So if at all, if you check this reaction, so the reaction is an iron and oxygen, it is forming Fe2O3 solid. So that is nothing but it is an rusting process. Clear? So the process is rusting. So we'll write it. This is the formula of rusting process. Now, so in spite of negative entropy of the negative entropy of this reaction, when you consider the entropy change is nothing but it is delta S. So delta S is minus 549.4. So rusting is a process which is spontaneous, already we have studied. So even though it is slow, but it takes place on its own. So because of which it is called as a spontaneous process. Clear? So in spite of getting negative, that is delta S is negative, then also the reaction is spontaneous. Why? That is the question. So if you check here, enthalpy of reaction for this reaction is so minus 1648 into 10 to the power of 3 joule per mole. So that is nothing but enthalpy of reaction. Some amount of energy is liberated here. Some amount of energy is liberated. So when this reaction is taking place, entropy delta S is minus 549.4 and delta H for the reaction is so minus 1648 into 10 to the power of 3 joule per mole. So it is an spontaneous process. If delta H is negative, so we can say that the reaction is exothermic in nature. Clear? So the when you consider a spontaneous process, spontaneous process means delta S total it should be greater than 0, not the delta S of the system. Whatever here it is given, it is for system they have given. Here whatever they have mentioned, that is for system they have mentioned, not for the total entropy. Clear? So that is the reaction taking place. Whatever the reaction is there, we call that one as entropy change of a system. So delta S for a system, it is negative they have mentioned. But if at all, if we have to say the spontaneous reaction means delta S total should be greater than 0. If the delta S total is greater than 0, even though delta S system is negative, if the total is coming as positive, then it is an spontaneous reaction. Clear it is? Now, how we are going to get that one, we shall see. So whatever the value they have given, that is delta S for the system, it is negative, that we have mentioned here. Delta S of the system is 549.4 we have mentioned. Delta S for surrounding we need to check. Delta S for surrounding, how to check? So when the reaction is taking place, reaction is exothermic in nature. So this much amount of energy is lost from the system. So we have a system taking place in a container. So in a container, all these reactions are taking place. So we have not container, we have on the surface of iron, this rusting is taking place. And the amount of energy is liberated to the surrounding. Clear? So some amount of heat is absorbed by the system, surrounding now, because it is exothermic process giving out heat. So surrounding is absorbing some amount of heat. Clear? So if at all, if it is absorbing some amount of heat, then so we can write the formula as delta S surrounding is equals to delta HF by T, or we can write Q by T also. Clear it is? Q by T also we can write. What is Q? Q we can write it as Q is heat absorbed by the surrounding. So surrounding is absorbing heat here. Clear it is? So how much amount of heat it is absorbing? So it is 1648 into 10 to the power of 3 joule per mole. So when we are writing this one, we should not write negative, because so here for this reaction heat is evolved. For the surrounding heat is absorbed. So we can write that one as a plus. So it is positive because so surrounding is absorbing the heat. Here the system, this is losing, so that's why it is negative. Here the surrounding which is absorbing the heat, so that's why it is positive. So magnitude remains the same, only the sign changes, and that is positive 1648 into 10 to the power of 3 joule per mole. So the temperature maintained is at 298 Kelvin. We have taken 298 Kelvin and we have mentioned. So the delta S for surrounding is 5530 joule per mole per Kelvin. Clear? So for system, what is the entropy change? 549.5 minus 549.4. So we have entered that one, and we have entered the delta S for surrounding also, and we got a positive value here. So delta S total is positive, so that's why we got this much. We got the value as a positive, so that's why we say that the reaction is spontaneous in nature. Clear, it is, the reaction is spontaneous in nature. So it indicates that so whenever we consider any process, or any system, any spontaneous reaction we are considering, we need to also consider the system as well as the surrounding. But the surrounding is very vast. So for every natural process or for any physical processes, you can't measure the entropy change of the surrounding, because leaving that system, remaining everything in the universe is a surrounding only. Clear? So leaving that system, remaining everything, whatever is there in the universe, entire thing we should consider as a surrounding. So to calculate the entropy change of the surrounding is very, very difficult. So for that reason, so second law, this is the limitation of the second law. So second law involves the surrounding also. So the surrounding changes also we need to consider. So that becomes a little difficult for us to calculate that one. So that's why that is one of the major limitations. And one more thing is, so it tells us about the spontaneity of the reaction. So but considering the spontaneity of the process, and this has to be dealt with, if at all, if it has to be dealt with chemical reactions, so we need to check the surrounding also, which is the most important difficult part in the second law of thermodynamics. So that's why we are going to introduce one more function. So one more limitation is there. So that is heat, whatever we have supplying the heat to the system, that heat is being converted as some amount of heat is being converted as work. The remaining amount is utilized for some other purpose, or it is wasted. But how much amount of heat is being converted as work, or how much amount of heat is being converted as useful work, that it doesn't tells us any idea about that one. Clear? It only says that some amount of heat is utilized as work, but what amount of heat is being utilized as work, or what amount of useful work is done by the system, it doesn't explains about that one. These two are the limitations of second law of thermodynamics. So we are going to introduce a new term, or we are going to introduce a new function, a new thermodynamic function, which gives the answers for all these questions. That is, we need to consider only the system. Surrounding should not be there. That is our one limitations of second law, which we have to overcome. And other thing is how much amount of useful work is done. So that is another thing. So these two things has to be resolved in the next law, or it will be resolved in the next law. Next law is nothing but third law of thermodynamics. Before going to third law of thermodynamics, we are going to introduce a new term, or new thermodynamic function. And what is that new thermodynamic function? So that the thermodynamic function is Gibbs energy. That is Gibbs energy or Gibbs free energy. Already you have come across this word in our equilibrium chapter. That is Gibbs free energy, or change in Gibbs free energy, that is delta G or delta G naught. Already we have studied. So here what is the meaning of that one, we are going to study here now. So Gibbs energy or Gibbs free energy we are going to use, and that Gibbs energy is one such thermodynamic function which helps in the development of the criteria of spontaneity or feasibility of the process. So it is going to help us in determining the spontaneity. So what are the conditions? We shall how we are going to explain the spontaneity, we shall see further. So Gibbs energy is also called as a free energy, or in general we can right? I mean, in general, we can name that one as Gibbs free energy also. So Gibbs energy refers to the capacity of the system to do the useful work. So Gibbs energy, that term indicates the system, how much amount of useful work is being done by that system. That is our major limitations of the second law. So that we are going to overcome in this. So that is Gibbs energy indicates about the useful work of the system. Clear? Now, so what is this Gibbs energy actually? Gibbs energy is defined as the amount of energy available from the system at given set of condition that can be put into useful work. That is how the system, how much amount of energy is there in the system. In that, how much amount of energy is exactly converted as useful work. So Gibbs energy gives an idea that, so even though the system might be having some thousands of energy in it, but in that 1000 kilojoule of energy, how much amount of energy is being utilized as a useful work? So that idea is being given by Gibbs energy or Gibbs free energy. Clear? So Gibbs energy tells us about the amount of useful work done. So we'll move on to the next mathematical equation. How we are going to relate this one mathematically, we shall see. So mathematically, Gibbs energy can be written as G is equals to H minus Ts. So G is Gibbs energy or Gibbs free energy. So H is nothing but enthalpy. T is temperature of the system, enthalpy of the system, and S is nothing but entropy of the system. Clear? So G is Gibbs free energy, enthalpy of the system, H is enthalpy of the system, temperature of the system, and S is entropy of the system. Next, H can be written as enthalpy can be written as U plus PV. So what is U? U is internal energy, P is pressure, and V is volume. So H can be written as H is enthalpy, enthalpy can be written as U plus PV. So we are going to apply the changing term for this equation, delta. We are going to apply the changing term, delta, for this equation. So apply delta on both the sides in the sense for G also and for this side also. So if the process, we are considering an condition here. So if the process is carried out at constant pressure and temperature. So now pressure is constant and temperature is also constant. So you can't apply delta for pressure and temperature. So for pressure and temperature, we can't apply delta. So then what it will be if you are applying delta, then how the equation changes? It is delta G is equals to delta U plus P as it is, delta V for volume minus T as it is because T is constant, delta S. Clear it is? So the equation changes to we are going to change that equation as so you can observe delta G is equals to delta U plus P delta V minus T delta S. So delta U plus P delta V can be written as delta H. So earlier only we can't write that one because P is constant. So if it is P delta V, then only we can mention that one as delta H. Clear? So remember both the formulas are very important. So this formula is also important as well as this one is also important. This equation is called as Gibbs-Helmonds equation. So delta G is equals to delta H minus T delta S. T and P are constant. That is what we have written that one as subscript indicates constant terms. So temperature is constant, pressure is constant. At constant temperature and pressure, delta G is equals to delta H minus T delta S, which is called as Gibbs-Helmonds equation. So we can say that the earlier one. So earlier one equation we can say this one as G is equals to H minus Ts. So this equation can be named as a Gibbs energy. So the equation can be named as Gibbs energy equation. And the next one, that is the delta G form of equation, is called as Gibbs-Helmonds equation. So remember this Gibbs-Helmonds equation. We have further how this delta G is related to spontaneity, and that part we are going to study in our next class.